Here's another interesting thing that happens with interference. When you have a thin film such as the outer skin of a bubble, or perhaps a wet spot on a parking lot, you see kind of a slight coloration like what you see here in this picture, in this slide. What causes that? That's what we're going to talk about here in this video. So we saw in diffraction patterns that path lengths differ from the distance from each slit to a particular point on a view screen. And because those path lengths differ, you're going to either have wavelengths that are in phase or out of phase. If they're in phase, you create constructive interference. If they're out of phase, you create destructive interference. You can go back to the previous videos to look at that. But here's another method. If you have a thin film of material that's only a few wavelengths thick, so we're talking on the order of micrometers thick, then light is going to reflect both from the bottom and from the top of that thin film. Both of those reflected rays are going to cause some sort of interference, whether constructive or destructive. If it's constructive, you're going to see a color. If it's destructive, you're not going to see a color. So again, you can see that in soap bubbles, oil slicks, and there are 100 other places where you could see them. Here's what's happening. You have light that's coming in from the sky, and it hits a layer, say a layer of oil, at point A, at which point some of that light is going to reflect. But the rest of the light is going to refract into the oil and continue down to point B when it hits a second surface, in this case water. And then it's going to cause a reflection from that second surface, and the light's going to come up, and you're going to see both of those light rays at the same time. And since you see both light rays at the same time, you're going to see some sort of interference pattern, whether it's constructive or destructive. Now, we need to look at a couple things here before we can actually analyze what's going to happen. When a wave is moving in from some index of refraction n1 and it hits a second index of refraction n2, you're going to have that wave reflect. Well, it turns out that if the layer that's causing the reflection is actually, if its index of refraction is greater than the incident angle of index of refraction, then the reflection is going to switch phases. Meaning, you see here that you have this light wave moving along, and you end up with a crest when it impacts the surface. But it hits N2, the reflective surface, and since N2 is greater than N1, it inverts the phase, so it switches from a crest to a trough, and then comes out reflecting at the same frequency, but with an inverted wave. But on the other hand, if the reflecting surface has an index of refraction that's less than N1, the incident index, then it's not going to invert the phase. It's going to keep the phase the same. So here we are with the same wave, hits your surface at a crest. Since N2 is less than N1, it reflects and starts off at a crest, same as when it hit N2. Okay, with that in mind, we can actually analyze the interference pattern a little more. So I zoomed in here on the air, oil, and water surfaces. Index of refraction of air is 1.0. The index of oil depends on the type of oil you're dealing with. I just picked one, I think it was olive oil, whatever it was. Oil is going to have an index of refraction somewhere around 1.45, 1.46, somewhere around there. And then water has an index of refraction of 1.33. So as light hits from the air, hits the oil, then the air is going to serve as N1 and the oil would be N2, then you have N2 is going to be greater than N1, in which case you're going to have an inversion of the phase with that reflection. So let me just go ahead and show what that looks like here. I'm going to just draw a couple of guidelines for myself. All right, let me draw a wave here. All right, that's a decent looking wave. So you have an incident ray coming from the air and hits the surface of the oil. Because the oil has a higher index of refraction than the air, it reverses the phase with the reflection, which means that since I have it hits the water with an amplitude on the right side of my guideline, it's going to reflect with an amplitude on the left side of my guideline. So it reflects that direction, looking with a wave something like that. But that deals with the reflection from the light hitting the surface of the oil. At the same time, you're going to have some of this light is actually going to refract into the oil. Now, I've marked here that the oil has a depth of 1/4 of a wavelength of light. Since I'm at an amplitude, 1/4 of a wavelength would take it from its max peak amplitude, bring it back down to 0. Forgive the scale, but it works. Okay, but now it hits a second surface between the oil and the water. The oil is now our incident substance, and the water would be our reflecting substance, so N1 to N2. And in this case, N2 is going to be less than N1. Since N2 is less than N1, the reflection is going to be in the same phase, which basically means once you have a reflection, it's going to pick up where it left off. So my wave was on the right and returned to 0 and moving towards the left. So the reflected wave continues. It's 1/4 of a wavelength from the surface of the water to the surface of the oil, which brings it to an amplitude on the left. And as it comes out, notice that they are completely in phase. Excuse me, that arrow was kind of crooked. That's okay. So on the reflection, both of the reflections are going to be in phase with each other. And since they're in phase with each other, you're going to have constructive interference. But now I can vary the depth of this oil layer. Let's change it now so that the depth of that oil layer is half a wavelength. So let me come back here, just as a reminder. Here N2 is greater than N1 between the air and the oil, and between the oil and the water, N2 is less than N1. Oh, I need my guidelines first. Just make it easier for me to draw. Okay, so here we go with, there we are. Nothing changes with the incident, with the original reflection between the air and the oil. Since N2 is greater than N1, it's going to invert the phase. And you're going to have a reflection that looks like this. But now, because the depth of the oil is different, the distance that my refracted ray travels allows the wave to progress a little bit further. So since it's half a wavelength, we go from one amplitude to the other amplitude. Okay? But since N2 is less than N1, it reflects in the same phase that it started, in which case it starts off here and goes half a wavelength, which puts it something like this once it reflects backwards, back up to the air. And it continues in this direction like so. But in this case, notice that the two reflective rays are out of phase with each other. The red line has one phase, so when one is at a maximum, the other's at a negative maximum. And in this case, you would get destructive interference. So point being, whether you get constructive or destructive interference totally depends on the depth of this thin film. So you can see similar effects taking place when you have shallowly curved pieces of glass. Here's a diagram of what's going on, and on the right you see a picture. And you can see regions where you get constructive interference and regions where you get destructive interference. And you can just see the light and dark patterns here. And that has to do with the varying thickness of the air layer between two sheets of glass. You can also do something similar. If you have two glass pans or two glass dishes of some sort, and you put them together, let's take a small something smaller than a pencil, a toothpick. Put a toothpick underneath one end. And if you can shine a particular type of just one light source from one point, get it dark everywhere else, and just have one light source, you would end up with a diffraction pattern that looks something like this. So how do you solve problems with interference? Excuse me. Problems dealing with interference in thin films is, first, you have to remember that interference occurs when you get two or more waves that arrive simultaneously at the same point in space. And so we're dealing with the reflection from the top of the top of the film and a reflection from the bottom of the film. And remember that you get constructive interference when those two waves are in phase with each other, and you get destructive interference when they are out of phase with each other. And then the last key to remember in dealing with problems with thin interference has to do with the fact that you have to add an extra half wavelength shift when light reflects from a medium who has a higher index of refraction than the incident index of refraction.